Students, welcome to the final section in this Unit 6, specifically for BC students, evaluating improper integrals. So earlier when we were learning about integration, one of the little caveats that I said is that you can only integrate over a defined domain. However, that veil is pulled back with BC. We can have situations where we're looking to integrate over situations where it's undefined at a specific point. So, for instance, you could have something as basic as the one on the right here, where basically you're going from 1 to 0, but clearly as soon as x is equal to 0 there, or the square root of 0, you're going to be undefined at that point. So we're wondering, basically, can I evaluate that definite integral? And as soon as we look at situations where you're approaching infinity, the question is, hey, does this have a specific value for its area, or is its area just infinity? So basically, an improper integral is where there's a clear break in the domain, or you're evaluating to infinity. So basically, this is kind of straightforward. All you need to do is you take your antiderivative like normal, and then you're going to basically take the limit as you approach those values and see if they do in fact evaluate to something. So for instance, taking the integral of from 0 to infinity of 1 over x, I realize that it's improper. So, and I'm sure they have this set up because it's more the notation that's important. Basically, because you can't actually evaluate infinity, we replace that infinity with a b, and we say, or a variable, and we say that variable itself is approaching infinity. And then you do the rest of the question just like normal. You ignore the fact that it is an improper integral until the very end, where you actually have to substitute it back in, and you ask yourself, okay, do I actually end up with some value here? So in this case, the natural logarithm of infinity is in fact infinity. It's a lesser degree of infinity. However, it's still infinity, and infinity minus 1 is going to give you infinity. So in this case, this is a divergent. It goes to infinity, or it could be going to a negative infinity depending on the context of the question. Another one, you can have a divergent that has no specific value, and so the classic example is if you ended up with a situation where you're taking sine of infinity or cosine of infinity. It's going to oscillate between 1 and -1, so it's not approaching some specific value or some bounded value. It's divergent. You can have a convergent improper integral. So in this case, if we look at this example, I'm going from negative infinity to 0. So again, I can't have negative infinity as one of my endpoints, so I say it's a, and then I rewrite this whole thing as a limit saying a is approaching negative infinity. And then I take the antiderivative of e to the x, which is just e to the x. And then when I actually go to substitute it in, I substitute the 0 in. The 0 goes there, and I substitute with the a, I substitute the infinity in. E to the negative infinity is just going to be 1 over e to the infinity, which is actually 0. And then 1 minus 0 is just 1. So in this case, we had a convergent improper integral. So what this is actually saying is that e to the x, from, if you think about that graph of e to the x, from 1 to negative infinity, like I'm just going to call that negative infinity there, so it starts really close to the horizontal asymptote and then approaches 1, that area actually evaluates to 1. Okay, so the area of the curve that's defined by e to the x, when x is less than 0, actually has a value of 1. Okay, so that's what we mean by a convergent definite integral. That area, even though we're talking about something that's infinitely long, which is kind of strange to think about, its area is in fact finite. And then we've got some practice there, but yeah, we can kind of do these out here, these first ones, just if we're curious. Let's pick one that looks like it possibly could be convergent, because the non-convergent one's a little bit boring. So clearly I can't have 0, so I'll replace this with b, and then I'll say this is 1, and I'll say the limit as b is approaching 0 for 1 over the square root of x dx. And just to make my life easier, I'm going to rewrite the square root of x 0 as x to the 1/2 negative dx. And then the antiderivative of that is going to be x to the 1/2. I don't see a negative 2 in front, so there must have been, or I don't see a negative 1/2, I should say. Sorry, this is my antiderivative. I don't see a 1, or I don't see a 1/2 in front, so there must be a 2 here to cancel out that 1/2. And then I'm going from b to 1. And so I'm just going to now substitute values in. So I'm going to say 2 to the 1 raised to the 1/2 minus 2 to the, what am I approaching? 0 there, 0 to the 1/2. So this is just 0, which means this value here is 2. Okay, so for this graph, from 0 to 1, for the function 1 over square root x, it looks like that it's, as it approaches 0, as it approaches 1 from 0, we have an area of 2. Anyways, that's it for this video, and if you have any questions, come find me in class.